Hello everybody. I promised you guys a follow-up video on the SPIM08HP 8 amp hour cells, LiPo cells from alarm hookup. These are 3.7 volt 8 amp hour cells. I'm sorry it's taken so long, but I've had to do a lot of testing on these to get them stabilized. So basically what I mean by that is that I had to charge each one of them fully and discharge them fully 6 to 8 times to get a final stabilized number on the capacity on them. And this is actually a good thing because they increased in capacity every time I charge cycled them. But I have 10 of these, and I'll put a link to these in the video description below for you guys so you can get them from Alarm Hookup on eBay. And it takes 12 hours to do a full cycle. In other words, it takes 12 hours to charge and discharge these. I was using a little AccuCell 6 Turnigy charger, and I've done all 10 of my cells now 8 to 6 times. Now you do the math on that. It's 120 hours to do one charge cycle on all 10 cells, and I've done it 6 to 8 times. So we're talking hundreds, almost 1,000 hours of charging and discharging these things to get the final amperage, what I call MAH hours of capacity on them. And good news is, well, I guess some bad news. I burnt this thing out doing it. So my little AccuCell 6 has had it. But I've got another one and it works great. So no problem there. I'll give you all the numbers on these. These are supposed to be 8 amp hours each. I didn't get a single one that isn't over 8 amp hours. Now your mileage may vary. He doesn't guarantee all of them will be over 8 amp hours, but all 10 of mine were. Also, they increased in capacity from my initial charge value or initial capacity test, 2.3% to almost 7.7% on the highest increase in value. So again, I can't guarantee you the same results, but I can tell you that every time I charge cycle these things up from 2.5 volts up to 4.2 volts and then drain them again, their capacity increased up to the 8 times on some of them, and some of them stabilized after about 5 charge cycles as well. But regardless, I'll show you all those numbers. I'll also show you the weights and capacities of these things, and then I'll put together a 12-volt battery and we'll test it out. All right, let's quickly get the weights out of the way here. We'll start with grams. I'll put one on here, and we have 284.1 grams, or in ounces, that is 10.021. So that's generally the average weight of these cells. So back again, 284.1 grams, 10.21 ounces. So next we're going to measure them up and then we'll go from there. All right, they're 5.5 inches wide. You can see that there. And we're going to go from that to metric and see what we are in centimeters. We were 14 centimeters wide, more or less. I'd say pretty well perfect. So 5.5 inches wide or 14 centimeters. And in height or length, whatever you want to call it. And I'm going to be measuring off from the top negative contact to the bottom positive contact. They are 21 centimeters in 21 centimeters in length, or in inches 8.25 inches in length. All right, so thickness, they're pretty thin. Let's find out what they're at. 8.41 millimeters thick, or 0.310 inches thick, 21.64 inches, 21/64 inches wide. So there's the thickness of these cells. Okay, let's get on to the capacities. All right, I want to point out something about these end contacts, the conductors for the battery, the negative and the positive down here. You can see there's a slight color difference in the two of them. This one's like a more copperish colored color, and it's thicker, and I think it's got some sort of copper alloy. I don't know if you can see the edge, but there is a copper tone to the edge. I'm not sure if we're going to capture it there, but it is thicker. And then the positive, as you can see, it's thinner metal, and it's more like a tin that I could tell. But here, I'm going to measure it out for us so we know what we're dealing with here. Not sure why they did that, but I'm sure there's some engineering reason. Okay, this is the positive lead. .283 millimeters on the positive terminal. Let's see what we get on the negative. I know it's going to be thicker. Absolutely has to be. Yeah, there you go. 0.309 millimeters. So yeah, it's thicker, stiffer, and again, I would be careful with these not to bend them too much. They're malleable, and they are, I'm sure, susceptible to metal fatigue. All right, here we are with my highest rated cell. It started off at 9,022 milliamp hours. It did grow when it was seasoned down to 9235 milliamp hours on the 8th recharge. That's a 2.3% increase in charge, and 12 milliohms for resistance. I've got the rest of them here listed, 8, 9, 8, 7 milliamps, up to 9119 milliamp hours, 1.4. Again, all of them have the ohms on them, as you can see. So basically the resistance, the internal resistance of the battery, the higher it is, usually that means that the less efficient the battery is going to be, or the older the battery is. Not necessarily, but basically it tells you, you know, how well the battery is going to work. So the lower resistance, the better. But these are all perfectly fine. So I'll bring up the next 4 that I have, and you can see those as well. Here's my last 4 cells, and you can see that they all improved again with cycling, you know, from 6%, 6.3, 6.8, I believe, 3.2. So yeah, you know, yours will vary as well, but that's what I got, and all the results are really nice. Internal resistance is 8 milliohms on this one, 48, 48, and 41. So those are a little higher, the last 3, but again, they still work great, and not really a big issue for me, because they still store a lot of energy. These cells are rated for 200 amps. If you saw Jehu's test, you saw that they went up to about 350 or so amps on a dead short, but I don't recommend that, because his actually destroyed the cell when he did that. But obviously they go above 200 amps, and in order to get that kind of amperage out of these cells, I would strongly suggest that you make as much contact surface with as much contact with the surface of these tabs on these cells to get the juice out of them. Okay, so don't just hook a little wire to it and think that's going to work. Try and use as much of the surface area as possible to get all the current out of these cells. They're very powerful, but the tabs are quite small, but they're wide, and you want to use something that gets as much contact surface on those tabs as possible. What I did is these bus bars that I made out of copper pipe, I cut them in half and then drilled them out into proper spots. This is not one that would do the job. You need a longer one with the holes in the right places. But this is an example of the copper bus bar I made from copper pipe, and it works great. And like I said, I cut it to the right size, drilled it in the right area, and connected the cells together to make a battery. So I'll show you that next. All right, here's my battery, my Franken battery. It's, you know, this is a very basic get it done configuration, so don't criticize me on my battery assembly or engineering. I just wanted to put it together safely and have it work. Right now this is a 4S configuration. You see the positive terminal here. Obviously I'm using my copper bus bar to connect to the tabs, and fully connecting you know, to the whole surface on the tab, so I get all the energy out of there with as much with as little heating as possible. And they actually stay quite cool when I was testing them. They you know, warm up a little bit, but not much. Here's the negative tab. take off on the other side of it. You can see here where I used, again, the copper bus bar to connect the two cells together, and I used a bolt, a nut, and washers on both sides, and I'll show you what that looks like on the other side so you can see it. I gotta be careful with these, I don't want to short anything. You can see here that I used a bus bar both on the top and bottom, connecting the two cells together, right? So there we have two cells connected together with two pieces of copper, top and back and front, so they get the most contact possible. You know, they're really secure. They're not going anywhere with these bolts on here. And I also put, if you can see, cardboard between each cell so that there's no chance of these, you know, surfaces shorting to each other. In other words, I don't want to create a dead short on these contact surfaces. I know this is Mickey Mouse, but that's the whole point, is to have a battery that works and is relatively safe for my testing purposes. If I was making a permanent battery, I don't think I'd build it like this. I'd probably find a better solution than what I've got here. And you can see that I've got cardboard between each one of them, and some tape too, just to protect them. Here's another look at the bus bar and how it connects two batteries together. Basically just compresses the two tabs together, and you know, with the nut and bolt configuration, and that works great. The nice thing also with these nut and bolt configurations is it gives you something to connect leads to, which I was doing with just a little meter that I have, an RC meter that I have here. You can just connect to the cells. I'll show you that, and it will monitor the cell as you're using it, which is neat. I like that, and I'll show you that when I'm testing the cell. And I also balance charge this using my Turnigy AccuCell 6 right here, and I connected those same leads to the balance charging port, this one here, and basically use this unit to balance charge it all the way up to its proper voltage. So that came out really handy, and I will show you, may show you how I connected all that so you can do it yourself. But again, 4S cell here. I'm going to take this fourth battery off of this and turn it into 3S and test it at 12 volts. Okay, hopefully you can see all of this telemetry. Got quite a bit. I've got my meter here. It's showing the voltage in the battery, 12.61. It's a little different here. I got 12.5 on it. So, you know, like I said, these are not the most accurate meters. Over here, I probably got around 12.6 as well on volts, as you can see on this battery tester, car battery tester. Not the most accurate thing in the world, but again, the only thing I got that does 200 amps or more of you know, testing. So I'm going to hit the button here, and we're going to see where this needle drops to in this green zone, and that should tell us how many cranking amps this little 3S 12 volt cell has. So let's hit the button and see what happens. We're into the 400, almost 600, just touching the 600, and you can see the voltage dropping quickly here. You know, but I got to let it go because the meter gets really hot when you do that. The car meter has a heating coil that causes that resistance to check the cranking amps, so I got to be careful with that. What do we got with temperature on that? Okay, 200. Well, whoops, got it in the right place. Yeah, 225 there. You saw 239. Check the temperature on my positive and negative terminals. Positive terminal, I got 78 degrees, and on the negative terminal, I got 80 degrees. And room temperature here is about 74. So it's slightly warmer, but nothing crazy. Again, we're back to 12.47 here on the meter, or you know, if you look here, we're a little different. What are we on here? 12.4. Yeah, we're close. And over here, we're basically reflecting the same thing. So look, I'm going to hit the button again. Don't want to overheat my battery tester. So here we go. Hit it one more time. And you can see we're into the 400s here, way above 200. So about 350, I'd say. 400, it's in that range. Not bad, right? So again, these cells do crank out the amps if you connect them correctly. Do it again. There we are, and you can see the sag over here. You know, Don't want to keep that button pressed too long. You see these temperatures? Yeah, I'm getting a little hot there. All right, 384. It was 400 there a second ago. I got on one of them. So yeah, you got to be careful. Yeah, so there's our result. We're doing pretty good here. Positive terminal is now at 81. Negative terminal 82. Probably get a little more out of it. 88. Let's see what the battery's at. I'll move this out of the way. Well, actually, I can't really say what the battery's at because this thing, the coil, as you can see, is smoking hot. I just almost burned my hand putting it on there. So not really fair to test the battery. It was sitting on 88 on the battery, I guess. But I'm sure that was being heated by this thing. That's a result from a 12 volt test. I may go hook this up to my car and see if it'll start it. I'll do that next. All right, I've got my battery set up. It's a 3S 12.6 volt battery. So it's got 3 cells in it, all set up in series, and it adds up to 12.6 volts. Current temperature of the car is 86.0 degrees, which is about the ambient temperature out here today. Yeah, I'm going to try and start it, but I understand this is 12.6 volts maximum, and the charging system on my car, I know, will charge the battery to 14.1. So I can't leave the car running. I'm just going to start the car to show that it has the amperage capable of starting the car, and then I'm just going to stop it. I'm going to hook up my battery meter here so you guys can see what's going on there, and we'll go forward with the test. But understand, this is strictly a testing bed. I would never recommend using a 3S battery like this on a vehicle, because it would, within minutes minutes, it would overcharge this battery and start destroying it. So 4S would probably be a better system, and then again, you need the proper charging system like a BMS and so on and so forth. So this is just strictly for testing the amperage and whether it's capable of starting the car with 3 cells. You can see right here that it's well within the 12.5, 12.6 range, so it's fully charged battery. Next, I'm going to start the car up, and you'll see that go down and then come back up again. But again, I will not leave the car running for very long. I don't want to overcharge this battery. Well, that worked quite well. It did dip down to about 10 volts, just above 10 volts every time you started. And I actually think it had an easier time turning the engine over than the headway batteries, but when I tested the headway batteries, it was considerably colder. The engine was considerably colder, so it would have been a little harder to crank. Now, as you noticed, when the engine was running, it quickly went to about 13 volts, 13.5 volts in charging. So you got to be real careful doing this. Do not use a 3S battery pack on a car, because it will overcharge the cells and destroy them. So at this point, yeah, very successful test. I'm going to cycle it about 5 times, just take a charge, and you can see now that the battery's right back to about 12.6, 12.5. So that's great. I'm going to cycle the car a few times. I started about 5-6 times, and then I'm going to take the temperature on the battery and give you those results, see how warm the terminals got and how warm the battery's gotten. I cycled the car, or started the car and stopped it 10 times to see what the temperature is now. The positive terminal at 94, negative terminal at 91, and the battery at 95. So not bad at all. And seriously, it starts the car up like if it's my original battery, like the battery that's in the car. It's very powerful. It doesn't seem to have any problem starting the car. And if I didn't know any better, I would think it was just my regular battery in the car starting it up. It just turns over real quick and starts every time. And after doing it 10 times, even then, it's still at 12.5 volts. Let's see if I show you that. There it is. There you go. You can see it, right? So this is an amazing battery, right? Let's give it a little crank test here. Oh, we're well into the 600 crank amps. So yeah, it's actually gotten better. Holy cow, look at that. So yeah, that's very impressive. Okay, so that's after 10 starts that it has that kind of power. These cells are amazing. So I would say at this point, very successful test. But again, my caveat being, do not use it as a 3S battery pack on a car, because your charging system will overcharge the cells and destroy them. Now, as a 4S pack, I'm sure it would work just fine. Again, it needs the proper charging system and the BMS to protect the cells. So again, this is just for testing purposes to see what kind of a load this thing can take and how well it works inside my vehicle. Works perfect. Okay, so we'll continue on from here. I'm going to test these batteries out, these cells, the SPIM08HPs. I have one here, as you can see. These are, what I got. I noticed that Jehu Garcia tested these, and he said that they were no good at 12 volts in a 3S configuration. But after watching his video, I noticed that there was a mistake that he made, and I don't know if he's aware of it or what the reason was. But he started the discharge at 11.20 volts if you watch his video. So I don't understand why he did that, but he said he got 36% of the battery was wasted. But let me explain all this. First of all, the SPIM08HP 200 amp hours, 200 amp max cell, 8 amp hour, 2.5 volt to 4.2 volts. So the minimum discharge point is 2.5 volts. The maximum charge point is 4.2 volts. So that means at 1S, it would either be discharged at 2.5 or 4.2. At 2S, it would be discharged at 5.0 and fully charged at 8.4 volts. And at 3S, it would be fully discharged at 7.5 volts or fully charged at 12.6. And like I said, Jehu started his test at 11.20 volts. So he left he didn't top up the battery when he was doing the test. So I'm going to top up a 3S, battery made out of these cells, and I'm going to take it up to 12.6 volts, fully charge it. And then I'm going to use my 1000 watt inverter I have right here. And, I'm going to do a similar discharge test. Now, that inverter, and what he was saying is the problem with the inverter is that you end up with wasting it because it doesn't go below a certain threshold. Now, my inverter has a nominal 12 volts DC, but the range is 11 to 15 volts DC. And if you look at the over voltage, okay, you can go up to 15.75 volts max. And you can go down to the low voltage shutdown, which is supposed to be 10 volts plus or minus 0.5 volts. So it could go to 9.5 or it could stop at 10.5. It depends, right? So the low voltage alarm is at 10.5, and again, plus or minus 0.5 volts. So what I'm going to do is I'm going to take that battery pack down from 12.6 to 10 point whatever, wherever it shuts off when the inverter says, okay, that's enough. I don't have enough juice to keep on running. And then I'm going to see how many amp hours and watt hours I get using my ammeter. And I believe it's more or less the same one he's got. And we'll see what we get when we actually go from the fully charged state of a 3S cell battery, using these cells down to the 10 volt shutoff on a power inverter. We'll see. Here's my SPIM 3S battery pack built. I've used 3 of these cells in series, the SPIM08HPs, and fully charged them to 12.60, 61, close to perfect. That's fully charged. That's where it should be when you're discharging it fully. I've got it hooked up to a ammeter here, and that's where all this telemetry is coming from. This is just a little hobby meter to check the cells. And from the ammeter, I go straight through into my inverter. This is a 1,000 watt power converter. It goes from 1,000 watts to 115 volts. And total amperage should be full load about 8.69. It does 2,000 watt surge, so we probably could do more if I loaded it up, but I'm not going to go there. I'm just going to load it, discharge the cell, and find out how many how many amp hours we get out of this battery. So let's zoom in on the telemetry here so we know what we're looking at. So there we are. We're at 12.61 volts, and you know, everything's zeroed out. It's ready to go. So I'm just going to hit it, and I'm going to discharge it until the power shut off on the inverter turns the inverter right off, and then we'll see how many amp hours we get out of that, or watt hours, depending on what you're looking at. There, we hit it. We turned it on. So now we're going to turn on the inverter. There we go, and it's starting to draw juice. May plug in a battery as well. Sorry, a light onto that. No, it's pretty high, 6.13. We'll go a little higher, I guess. There we go, 8.5, 8.41. That's pretty fair. We'll let that go. I'm going to discharge it all the way down, and then we're going to see how many amp hours we get out of this cell from a fully charged state to a fully discharged state for the inverter anyways, which should be around 10 volts, you know, roughly. All right, the power inverter is starting to complain about low voltage, but it's still kicking. Let's see when it cuts off. Oh, just cut off. So it no longer is supplying juice. So let's turn that annoying sound off there. All right, what we got? We got cut off around, I don't know, 10.25. We've got a low amperage, 0.78 amps. It's some circuitry on the actual inverter still drawing a little bit of juice, obviously. But total amp hours is 7.582 amps, or 7,582 milliamp hours. So awesome on that battery pack. 84.771 watt hours. 4 hours and 39 minutes is how long I ran it for, but I mean, it depends on what kind of load you run. I was running a laptop as a load, so that's variable. It goes up and down. So, you know, it's up to you. It's up to you to figure out how long it's going to last for your application. But gee, you know, like, we got 7.58 amp hours out of this thing, and there's still charge left on the batteries, as you can see here, 3.52, 3.51, and 3.49. Now this thing's not all that accurate, but it's pretty balanced from that point of view. And so what I'm going to do next is going to take this down from where it is now and fully discharge it with my balance charger all the way down to, you know, where it cuts off, and then we'll see how much is left on the how many amp hours are left on the battery pack. And between the two, we should be able to add them up and get a total. But boy, right at this point, I would say that's a really excellent 12-volt battery pack. So yeah, I know, like I said, I love Jehu Garcia. He's great. I watch a lot of his videos. He knows what he's doing. But on this one, he missed it, because I don't think he noticed that he only charged the battery pack to 11.20 instead of, you know, 12.6, which would have been the maximum. So let's go discharge this fully, see how much is left on the actual battery pack using my balance charger. And again, all this stuff I'm going to put links to in the video description below. I got the battery packs from Alarm Hookup on eBay. I'll put links for that in the video description as well. So let's do the discharge, see what's left. So here we have my Turnigy AccuCell 6, and we're going to use it to discharge. You can see here on the screen that I have my SkyRC software, which is connected to this balance charger. So basically you can see what's going on. So let's hit the start here. All right, and it begins, and you can see the three cells you know, showing pretty even numbers, 350, 353, and 353 on the third. So two exactly the same, and here you can see the status. 349, 342, 352, 352. So yeah, it's a little different than what you see on the screen. I've always noticed that with the software. I don't know why, but you know, the end voltage is going to be 7.5 volts, 3S. So we'll let that go. And it says currently that it actually has 9% of the fuel. So if that's true, we used 91% of the cell's capacity in discharging it with the power inverter. And I would say that's a great power pack for a 12 volt system. So we'll see what we get when we're done here. So here's what was left on the cell after the power inverter shut off. You see we got 952 milliamp hours, so 0.952 amp hours. You know, it's the whole battery discharged down to 8.44 volts before the balance charger shut the process off, because as you can see, cell 1 was at 2.51 volts, and the charger's not going to discharge it all the way down past that point. So it stops there. It's supposed to do that, so that's a good safety feature of it. But basically, it did exactly what it was supposed to do. You can see the curve there. That's the voltage curve. You can see here the current graph doesn't really mean all that much. And let's go do some math on this so that we can understand what happened here. So total milliamp hours for this whole cell, doing some math here, the 7.58 amp hours and the 0.52 amp hours. So the 7.58 was the original discharge on the inverter, and the 0.952 amp hours was on the actual balance charger. Now, total is 8.536 amp hours, which is perfectly, within what the cells are supposed to be, or 8,536 milliamp hours for the entire battery. So, and if you do the math here, you see that 11% of the total charge was not used by the inverter. I think that's excellent. I don't see any problem with using these cells for a 12 volt system whatsoever. And to be fair, I did let the battery sit for a bit, probably about 45 minutes, between the time that the inverter stopped taking the charge and the time I did the discharge using the balance charger. So, there's a little bit of recovery there. So I would say the total charge not used is probably closer to what I first saw on the actual balance charger, which was about 9%. But this is as accurate as I can be with the test I did. So yeah, I would say I would have no problem recommending a 3S a 3S battery pack using the SPIM08HP cells. In fact, I'm really impressed by these cells. So yeah, that's it. So I'm just going to take this now and wrap it up. Here's a discharge curve on that battery pack, the SPIM08HP 3S configuration that I used on my inverter. And you can see why this is a good system for a 12 volt inverter, because first of all, you get a pretty solid discharge curve all the way down to about 10.6, and then it dive bombs to the bottom. And our converter or inverter shuts off at 10.28 volts approximately, I believe. So you can see that would be around here somewhere. And again, most of the charge in this battery pack will have been used up by this inverter before it shuts off, but it will never fully discharge the battery pack because it doesn't go down that low. So it's perfect for a 12 volt system, or at least one with an inverter like mine. So yeah, this is I have no problem recommending this battery pack or these cells for a 12 volt 3S battery pack. I'd say they're optimal for that purpose. So yeah, I think Jehu messed up there because he didn't fully charge the battery pack to 12.6. So yeah, this is the reason why this works so well. Well, as you saw there, you can see that these cells do a great job in a 12-volt battery pack. The SPIM08HPs are available on eBay from Alarm Hookup. I'll put a link to that in the video description below, so just click on those links and go get yourself a set of these. They're available for four of these are available for $29.99, so $7.50 each. I don't think you can beat that anywhere as far as a battery value. I think it's great. For a 7.5 to 8 plus amp hour cell, I think they're awesome. Yeah, that's my roundup on this. I would say no problem recommending these for a 3S 12-volt battery pack, especially using an inverter like mine. I think it's a very good match, and the value is superlative. You can't beat it. Okay, so again, everything will be in the video description below as far as links for the gear and equipment I used, and especially these cells at on eBay from Alarm Hookup. Definitely get yourself some of these if you're working on a project like this. Okay, that's it for my video. If you like this video and it helped you out in some way, do me a big favor. Click on the thumbs up button here on the bottom right hand corner. Give me a thumbs up. It helps my video, helps my channel, and I greatly appreciate it. Also over here somewhere you'll see a picture of me, and that is a subscription link. Click on that subscription link to subscribe to my channel. You'll also get a second option there, which is the bell icon. And when you click on the bell icon, you'll be notified every time I put up a new video, and then you can watch that at your own leisure. All right, just like always, I want to thank you all for watching and for your time.